graduate students from Shanghai Jiaotong University. I am Chen Yubin, and this is my partner, Zhuocheng. Today, we will talk about the distributed QEMU. In this talk, we start with a demo show. We will introduce our motivations of building distributed QEMU, and then we will introduce the implementations of CPU, I/O, and the memory virtualizations in distributed environment. Furthermore, some experience results are given to show the potentials of distributed QEMU. We will show a demo here. The main purpose is that distributed QEMU run guest OS on multiple machines, which provide a consistent view with huge amounts of hardware resources. In this demo, we want to set up a VM with 32 cores on 2 machines, which each machine runs KVM instance and provides 16 cores. Now the guest OS begins to boot. Once we have logged in, we could use the list CPU to show the guest OS truly has 32 workers. We can see that the worker, and then we can run the workload with 32 workers. We can see that the workers are dispatched to different cores on the 2 machines. And we can use the edge top on the host machine to inspect the result utilization. Okay, so why do we need to make QEMU distributed? Big data applications and the machine learning force people to handle the data they have collected. However, those data are hard to handle in a normal machine. This is simply because they need a lot of CPU, I/O, and memory resources. Today, the conventional wisdom is that traditional scale-up solutions, such as mainframes, has low cost-performance ratio and physical limitation. In the same time, the data processing frameworks such as MapReduce and Spark are proposed and quickly become prevalent. However, those distributed frameworks bring some programming model complexities and runtime overhead. Furthermore, some programs cannot be rewritten to this style. In order to solve this problem, we represent the concept of distributed QEMU. It is a hypervisor which enables guest OS running on physical machines with a consistent hardware abstraction. So guest OS can make use of CPU, I/O, and the memory resources of those machines. In this figure, we show an overview of the distributed QEMU. Each machine has a QEMU KVM instance, which manages local resources. vCPU is managed locally, while the memory is managed by the distributed shared memory protocol. For each I/O device, there is a master machine. Other machines just forward the requests to the master of this device. But there are some challenges in building the distributed QEMU. The first one is how to implement the communications between vCPU and I/O devices on different machines. The next one is how to keep synchronizations of memory and the time among different machines, since the guest OS is now running on the distributed environment. We will show the solution to those challenges. Let's begin with the CPU virtualization. In our design, each QEMU creates a full amount of vCPU threads. We divide them into local vCPU and the remote vCPU. Local refers to the vCPU running on the local machine, while the remove refers to the vCPU running on other physical machine. Local vCPU thread behave as usual, while the remove vCPU thread is dummy and never dive into KVM. Therefore, only specific vCPU thread will run on physical CPU of each machine, which visualize the distributions of vCPUs. As we have shown in the demo, vCPU 0 to 15 are located on the machine 0, and the rest vCPU are located on the machine 1. For machine 0, vCPU 0 to 15 are local vCPU, while the others are removed vCPU. Now we have distributed vCPUs to different machines. The next thing to be considered is the IPI forwarding. The overall strategy is straightforward. If the IPI is sent to the local vCPU, then we just process it as usual. Otherwise, we send it to remote QEMU and inject it to the APIC of the target vCPU. For example, vCPU 0 located on the QEMU 0 send an IPI to the vCPU 1 located on the QEMU 1. So QEMU 0 should forward this IPI to the QEMU 1. However, there is a detail of APIC that makes things more complicated. On x86 platform, all IPIs are implemented as broadcast message under the hood. After receiving an IPI message, the CPU uses 3 special registers of API-C to determine whether it is the destination of this IPI. But in a distributed environment, we cannot check the LAPI-C of removed vCPUs. So we initialize dummy API-Cs for removed CPUs to provide those 3 necessary registers. Whenever a local vCPU modifies one of those 3 registers, it will do a broadcast to make all dummy API-C up to date. Then the removed QEMU could know the target of an IPI and inject it accordingly. In this way, IPI forwarding implements the interrupt injection. In QEMU1's view, it behaves as the same as receiving IPI from a local vCPU. In addition to the IPI forwarding, the interrupts sent from I/O devices to vCPUs also need to be forwarded if the vCPU and I/O devices are not located on the same machine. On x86 platforms, there are 2 ways for devices to send an interrupt, that is through IO-API-C or MSI. One important difference is that multiple legacy devices share one IO-API-C, while each modern PCI or PCIe device configures and generates interrupts on their own. The interrupt forwarding process for IO-API-C is shown in this figure, as there should be only one IO-API-C per system. We dedicate one of QEMU as master. Other QEMU maintain the dummy IO-API-C to collect those interrupt signals and forward them to the master IO-API-C. Reads and writes to the register of IO-API-C are all routed to the master IO-API-C. So it contains all the necessary configurations and is able to generate interrupts once the forward signal arrives. Also, IO-API-Cs requires an end of interrupt message from CPUs for level trigger interrupts, while MSI does not. So we also need to forward end of interrupt message to the master IO-API-C when necessary. For MSI, things are much simpler. If the access to the PCI configuration space are properly forward, the MSI of this device will be configured correctly. Then all we need is to forward the interrupts to the removed vCPU when an MSI is generated by this device. The next part is the I/O forwarding. Generally, I/O devices are accessed and programmed through MMIO, while on x86 platform, there is an additional I/O address space that can be only accessed through special PIO instructions. Once the vCPU performs a PIO or MMIO, it will trap to KBM or QEMU accordingly. When KBM exits due to a PIO or MMIO, we add a check. If the PIO or MMIO is to the removed device, we will forward it to the removed QEMU. After the access is processed on the removed side, a reply is sent back, and then we can finish this I/O access and return to the guest mode again. For PCI or PCIe devices, the situation is more complicated. Each device has its own configuration space, which is accessed indirectly through the PIO. We need to distinguish access to the configuration space of local and the remote devices and forward accordingly. Further, the MMIO memory regions is dynamic config. We need to broadcast this configuration so that we can distinguish MMIOs to remote devices and legal MMIOs. Next, we will talk about the memory and the time synchronizations of distributed QEMU. My partner, Zhuocheng, will talk about this.
So let's talk the virtualization of memory, since I've contributed much to this part. So basically, the main challenge is to maintain a consistent view of memory for multiple machines. To achieve this, we've implemented a classical distribution memory in KVM to provide the coherent memory required by guests. As guest is not well hypervisor, so we cannot use explicit message passing to maintain consistency or use modern DSM variants that allow or even enforce clients to do manual synchronization to improve performance. So this is the reason why we choose to use classical DSM solution dating back to 1989. And we try to use RDMA network to speed up it. So for those who are not familiar with DSM, I'll give a brief overview of it. Basically, we have 3 states: modified, shared, and invalid associated with each page, and they're controlled by EPT. If a page is in modified state, it indicates exclusive ownership of this page and have read and write privileges. If a page is in shared state, then it is potentially owned by multiple machines and is write protected. If a page is in invalid state, then it means the current QEMU instance does not own a valid copy of this page, and then the corresponding EPT entry is marked not present. So our operation of DSM follows a simple MSI protocol. That is, when a guest tries to write a shared or invalid page, then it will first retrieve the latest copy of this page, and then complete write the invalidate or the current copies of this page, and then set the state to modify. If the guest tries to read a invalid page, then it will first retrieve the copy and then add this requesting page to the copy set of the owner of this page. Well, I mentioned the owner and copy set. Well, the owner of a modified page is itself, and for shared page, for the copies of a shared page, we designate one of the copies as the owner and set it and maintain a copy set of those copies at this page, and then we have managers to track the owner of those pages. Each machine is responsible for a portion of guest memory and is manager of this memory. So let's look into detail for shown in these 2 figures. The first step is that guest, since we have set those privileges in EPT, when the guest tries to write to a shared page or access an invalid page, then it will first cause an EPT violation, and then the execution is transferred to KVM, then intercepted by our DSM. Where if the manager is owner, we can just retrieve the page from the manager, and if not, we can delegate the request to the owner and get it. So basically, there are 2 situations. If it is a read, then we should just add the requesting page to the copy set of the owner at this or this step. Then if it is a write, we just transfer the copy set of the old owner to the new owner, shown as the blue line in these 2 figures, and then invalidate all the copies of this page right before we return to guest mode. So basically, this is the basically we till now we have given a review of DSM, and here are some interesting things that we've encountered in the attempt to implement this DSM in KVM. Well, since there are some difficulties due to the complexity of the KVM memory subsystem, but more importantly, we found that mapping management, the first challenge is that the mapping management in the presence of virtualization is quite different from those in traditional DSMs. That is, you know that QEMU allocates the guest memory in its virtual address space and registers it to KVM. So essentially, we have the only shared space we have is the guest physical address space. So we should use the GPA address in our internal messages of DSM. And one may think that we should associate the states and copy set with pages in GPA space. It turns out it is not like this because there can be some pages in HBA space that can correspond to multiple pages in GPA space. Or worse, in x86 architectures, basically essentially every page in HBA space corresponds to 2 pages in GPA space because of the SMM pseudo GPA space. So we maintain state and copy set of pages in HVA space and maintain the reverse mapping from HVA to GPA pages. And when we try to change the state of a page in the state of an HVA page, we will change all the EPT entries of those corresponding GPA pages. And then the second challenge is that there can be memory accesses bypassing the protection provided by EPT because, well, the guest memory is allocated by QEMU, so QEMU and KVM can manipulate these guest pages directly. So the solution is to add pin and unpin operations exposed as DSM main pin IO control to QEMU. Those are basically locking operations. For example, if we want to operate on some page, then we first pin it, transfer it to our desired state, and block all incoming requests on this page. Then we can do anything we want to this page, and then unpin it, blocking all the incoming requests on this page, and proceed as usual. Well, another thing is time synchronization. Well, at first, we haven't considered it only to find that some time-related system calls, such as sleep, did not behave correctly. For example, sleep would sleep for longer than we requested. It turns out it is fault of KVM clock. KVM clock is a virtualized clock device that runs at a constant rate of 1 GHz, usually used by gas OS as the primary clock source. So since QEMU tries to initialize the KVM clock to 0 upon startup, we have different offsets of KVM clock in different instances of QEMU, result in a clock scale problem. So our solution is to make QEMU query for the value of KVM clock of the master QEMU, that is the first started QEMU, and then get this value and apply it to the KVM clock of the current QEMU. So this way, all vCPUs will see the same value of KVM clock.
Okay, that's our design of distributed QEMU. Then we will talk about the performance. The distributed QEMU is able to run popular Linux distributions as guest OS. We conduct a series of experiments on our prototype with below configuration, including a user network adapter for TCP network and HCA for RDMA network. We have two purposes on experiments. The first one is running some benchmarks on different guest OS using the distributed QEMU, comparing running with them in the Spark and measuring the time consumption. We run SB6, Linux, and Spark with same configurations on 3 benchmarks. The green bar represents the SB6, the blue bar are Linux, while the orange bar are Spark. We find that in some cases, distributed QEMU outperforms Spark even when running on Linux. The second one is providing the time spending on each part of VM to identify the performance bottleneck of this system. We find that the interrupt or I/O forwarding span time is less than 1%, while the most time spent in non-root mode means that the guests do some useful work. So the bottleneck is exactly the page fault of the distributed shared memory. Then we compare the time consumption when using the TCP or RDMA network. The green bar represents the RDMA, while the blue bar represents the TCP. Lattices in the bottom box is the ratio that distributed shared memory page fault occupies. When the page rank with a TCP network spend about 50% of time on distributed shared memory page fault, the page rank with RDMA network only spend about 25% of time. So we can conclude that fast RDMA network is necessary and can potentially make distributed QEMU practical enough for real-world use cases. To sum up, we try to extend QEMU to support guest OS running on multiple machines with a consistent view. We deal with virtualization issues about CPU, I/O, and memory in distributed environment. Our experiments show the potentials of distributed QEMU. At the last, we will discuss some future works of distributed QEMU. Firstly, we now disable the dirty and access-based support of EDT. When this feature is enabled, any access to the guest page table, including the page walks performed by the hardware, is considered by EPT as a write operations, and when the GPA to HPA translations happen. The results turn right for will cause page threading and ruin the performance, so we have to disable this feature. Secondly, support the IRQ chip in the KVM. Now we have implemented interrupt forwarding in the QEMU, which need to configure IRQ chip in QEMU and make more access from kernel mode to user mode. In the future, we will port the interrupt forwarding mechanism to the KVM. Thirdly, support distributed I/O devices. Currently, we simply put all the devices under the master QEMU and direct all PIO or MMIO to it. In the future, we will support making use of I/O devices from the other QEMU. The most challenging thing is for tolerance. If one or more machines suddenly break down, then we should find a way to catch and handle it. That's all we want to share with you. This is the homepage of our project, and we will upload the code to there later. So thank you. Any questions?
Your point about the mapping of HVA and GPA addresses,
Yeah.
that is the same problem for things like migration, have the same problem with that. And the way that we solve it in migration is that we always migrate RAMs, indexing them off the RAM block that the RAM accesses. And so if you always use a RAM block and an index within the RAM block, that is unique within the QEMU address space and is independent of the HVA. So it's the same problem there. My other question was, have you looked at older things like Hakatana-share, which did something similar a few years back?
What?
So there's been a few attempts to do DSR. And how does yours compare to the other implementations?
Actually, we have no C before, and we will see after that.
Okay, I'll point you to some other implementations.
Okay.
Okay, hi. I was actually wondering if you compare the performance to standard Linux clustering, well, standard, semi-standard. You can get multiple Linux kernels talking to each other directly on the guest level. So that has been around since, I don't know, 20 years ago.
Sorry, I don't get your point.
Okay, so I was wondering if you compare the performance with Linux clustering, basically running two QEMUs with guests that talk to each other instead of QEMUs talking to each other.
So we can talk about it later. Okay.
Okay.
What about TSC synchronization?
What?
TSC. Did you see any issues with synchronizing TSCs across multiple hosts?
Okay, we have considered it, but we haven't implemented it yet. Since TSC can already desynchronize in some environments in real hardware, so the Linux host, the Linux guest can deal with it. In most cases, most applications can perform as well as usual and do not get some problem.
So thank you.
Okay, thank you.